Okay, calculus class. You see my backdrop. I really like Buffalo. Yeah, I don't know, maybe something about the mountains and the west and whatnot, but that's my backdrop. Something else I really like is calculus, and I just want to encourage you that again there are three really big ideas: limits. We're not done with limits, but you've done most of what we need to do with limits so far. And then the second idea is derivatives. And the third idea is integrals. And the fact is that as you examine these three pieces, we're kind of done here. We're going to start this today. And derivatives is a really cool idea. And the word calculus actually comes from the word calculate. And the ability to calculate the infinitely large and the infinitely small. And that's a really cool thing because this whole idea of infinity or 1 over infinity, it really boggles our minds. And it's something we're challenged with. And even more than anything this year, maybe you're thinking about your grades, your GPA, your ACT scores, your class rank, stuff like that. More than anything, I just really hope that you guys set aside that these will someday go away. They'll all go away. Someday people won't necessarily be concerned about your grades or your class rank or your GPA or your ACT score. You're going to show up in college, and what you are really able to bring with you is what you know. And I want you to dig deep into this calculus idea. What is this thing that we call calculus? Um, and that's what we're going to investigate today. It's really the first big idea, but remember that at the end of the day, if you got a good GPA but you don't really know what you're doing, um, maybe we as teachers didn't measure that learning very well, then you're in rough shape. That ACT score isn't always exactly what you know and what you're going to bring with you in terms of calculus. So focus on that learning piece and just digging deep into this big idea and really embracing this venture into calculus. I just want you to know that geometry was really the kind of first idea of mathematics that the world developed, and from geometry we had these cool ideas that came forth. Trigonometry comes from geometry, and really another thing that comes from geometry is this thing called calculus. And you're wondering, like, where does algebra fit into all this? Well, the thing is that algebra wasn't developed until you know hundreds of years later, after geometry and trig and calculus, and it was really done so that we could do a better job with calculus and trigonometry and those things. So algebra is kind of just the language that we use to describe ideas of calculus and trigonometry and geometry. So that's really just to support our work. So I know that we've left kind of this algebra piece to some degree. There is algebra that pops up in calculus, and you're going to see that today. But really, calculus is a study, kind of like geometry or trig is. Algebra is just the language we use to be more efficient. Today, the big idea that we want to talk about is the slope of a tangent line. And so, if you consider a function, f of x, and suppose that we have a point at A. And the question is, what is the slope of that tangent line? Well, this is tricky. And the reason why it's tricky is because in order to find slope, we always need 2 points. And in this situation, you just have one. You have point A. You have the y value, the x value is a, the y value. If we plug a in, we get f of a. So that's our coordinate. What is the slope of that tangent line? Well, this is where we build in calculus and the idea of limits. And we're going to show you. The truth is, I really can't find the slope of that line tangent at one point. I have to have 2 points. So I'm going to go ahead and create another point that has another line. We're going to say that that point occurs at a value of x. Therefore, the y value is f of x. And we're going to call that line the secant line. Now, as you look at that, how would you compare the slope of the secant line to the slope of the tangent line? As you look at it, it looks like the slope of the secant line is greater than the slope of the tangent line. I think that that's pretty obvious by looking at the drawing. So the slope of the secant line, if we could find that, that would be a decent representation for the slope of the tangent line, but it's not exact. What we could do is we could bring that point up there and we could bring it closer. Say we bring it down here. Now let's say we call that x instead. And this value is f of x. Well, I'll draw that one in green. Now if you look at the slope of that secant line, the slope of that secant line is even closer to the slope of the tangent line. Well, how do we find the slope of the secant line? We take y sub 2, which is f of x, minus y sub 1, which is f of a. We divide it by x sub 2, which is x, minus x sub 1, which is a. That's the slope of the secant line. In order to find the slope of the tangent line, you saw how for the secant line we drew that point closer. So if we draw x closer to a, then eventually the slope of the secant line is going to become the slope of the tangent line. Well, how do we draw x closer to a? Very simple. We use a limit. And that is called definition 1. The slope of a line tangent at one point on a curve. Now, what's really interesting is if you were to plug in a into this expression, you would get f of a minus f of a over a minus a. So you can see the algebraic representation gives you a 0 divided by 0. You know, I think that that's something to be noticed because we've come up with a lot of 0 over 0 situations already. But this picture, this diagram, it's something that you really should be able to focus on and be able to understand, be able to regurgitate. This idea of the secant line slope becoming the slope of the tangent line, very powerful. And so let's look at this one. It says, find an equation for a line tangent to the given function at the given point using definition 1. So if I want to find an equation for a line, I need 2 things. I need the slope, and I need a point on the line. In this situation, we're going to use an x value of 1. And if you plug 1 into the function, you get a y value of -2. So I have my point, it's already given. The way that I find slope is I use the limit as x goes to my a value, or 1. I'll write it up here, the limit as x goes to a of f of x minus f of a, all divided by x minus a. So f of x is x squared minus 3. We're going to subtract f of a, or -2, divided by x minus a, or x minus 1. So we have the limit as x goes to 1 of x squared minus 1 over x minus 1, or the limit as x goes to 1 of x minus 1 times x plus 1 over x minus 1. You can notice in this situation that the x minus 1's do cancel. And as I plug in 1, I get 2. That means that your slope is equal to 2. Now that I have a slope of 2, I can write my equation for my line. Y minus y1 is equal to m times x minus x1. Or y plus 2 is equal to 2 times x minus 1. So y plus 2 is equal to 2x minus 2, or y is equal to 2x minus 4. That's the equation of the line tangent. You should be able to have an understanding graphically of what this looks like. So the graph of x squared minus 3, you know it's shifted down 3 units. And if you just look at it, if I have a coordinate of 1, negative 2, you should say, well, does the slope look like it could be 2? Well, sure. You know for sure it's going to be positive. But what's really cool is if you take out your calculator and you graph these in the same window. I turn my calculator on and I look at it and I type in x squared minus 3. And I type in 2x minus 4. As I look at those graphs, you're going to see the parabola produced first, and then you're going to see a line. And sure enough, it does touch tangent at just one spot. And so you've connected these big ideas. The infinitely small. When you take x and you draw it closer to a, the distance between x and a becomes infinitely small. Infinitely small is the distance between them. And so being able to calculate slope, instead of using 2 points, and it makes it work out quite beautiful. Look at the next one. Same type of situation, we just have a cubic. I need slope. (23). In order to find the slope, I take the limit as x goes to 2 of f of 1 minus 23, all divided by x minus 2. Or the limit as x goes to 2 of 3x cubed minus 24 over x minus 2. Look for my common factor. We have the limit as x goes to 2 of 3 times x cubed minus 8 over x minus 2. That is the difference of cubes. And you all know, because you've practiced it now, that the difference of cubes does factor to x minus 2. And then we square the front. We square the back. We multiply the two together. The last part is always positive, and this is opposite what the front is. Divided by x minus 2, you can see how those cancel. Now, squared is 4. 2 times 2 is 4. So 4 plus 4 plus 4 is 12. Times 3 is 36. And so y minus 23 is equal to 36 times x minus 2. You could go ahead and put that in slope-intercept form, but that's the idea. That's the idea. Okay. We're not going to do example 2a or 2b, and we're not going to use definition 2. I'm going to change that from the notes we had last year. We're going to continue to use definition 1. And here we have a square root function. And so again, I have a slope and I have a point. And the point is going to be 6, 2. Notice that if you plug in 6, you get 6 minus 2 is 4, and the square root is 2. In order to determine the slope, I take the limit as x goes to 6 of f of x minus f of a divided by x minus a. Remember from the work we did with limits that in order to solve this, what we do is we multiply by the conjugate. X minus 2 plus 2. Or square root of x minus 2 plus 2. And so we have the limit as x goes to 6 of x minus 2 on top. And then, did I make a mistake here? Sorry, it should be x minus 6 on the bottom, shouldn't it? Sorry about that. And then minus 4 up top over x minus 6 times the square root of x minus 2 plus 2. Or the limit as x goes to 6 of x minus 6 over x minus 6 times the square root of x minus 2 plus 2. Notice the x minus 6's cancel, and you're left with a slope of 1/4. And so we would have y minus 2 is equal to 1/4 times x minus 6. And again, I'm trusting you can put that into slope-intercept form. Sorry about my mistake there with the 6. And finally, the last one. And again, as you mature as a mathematician, it'll be very good if you can anticipate a little bit about the graph and the answer. So I know that you realize what the graph of 1 over x minus 1 looks like. So right away I'm visualizing this in my head, and I see that I have a point of 3, 1/2, or maybe something right over there. So I'm thinking that I should have a slope that's negative, and it looks like it's going to be a value that is bigger than -1. So maybe like -1/2, -1/4, something like that. That's my guess here as I'm just kind of looking at it. Let's see what we come up with. We have a point on our line, which is 3, 1/2. Our slope, we take the limit as x goes to 3 of the function 1 over x minus 1 minus f of a, or 1/2, divided by x minus 3. Limit as x goes to 3. I want to find common denominators, so I multiply top and bottom by 2, top and bottom by x minus 1. And I get 2 minus the quantity x minus 1 over 2 times x minus 1 over x minus 3 over 1. Watch what happens. Limit as x goes to 3 of, this becomes 3 minus x over 2 times x minus 1. I'll multiply it by the reciprocal. And if you notice, if I factor out a negative, these two will cancel. Plug in 3, and we get -1/4. So therefore, y minus 1/2 is equal to -1/4 times x minus 3. Or y minus 1/2 is equal to -1/4 x plus 3/4. I can rename the 1/2 to be 2/4. So y is equal to -1/4 x. If I add that 2/4 over, I get plus 5/4. And again, for me, the most satisfying thing is to be able to take out my calculator, going into y equals 1 divided by the quantity x minus 1. That is my function. I graph that, and we anticipated that the graph looked like that. I would like to zoom as a decimal just as I zoom in here and get a little bit better picture. That looks like kind of the picture that I produced. And then we want to see if the line -1/4 x plus 5/4 is in fact the equation for the line tangent. So this is a way for you to always be able to check your answer. Just simply graph them, and if they're tangent, then you're good to go. If they are not tangent, then you know you made a mistake. And you can see it just does touch once right there. It's beautiful. A very complicated problem, but yet we made it very simple. The idea of finding the slope at one point on a curve, calculus using the form of limits, makes it easy. So we have these big ideas. You're just starting the idea of a derivative by looking at the slope of a tangent line, this idea of having infinitely small distance between x and a, and it's a pretty cool piece. So that should be enough to start your assignment. Hopefully the sound quality works well for you. And right even at about 20 minutes, we'll stop it there. Have a good day.